Our next speaker is Professor Seth Goytema from the University of Michigan. Professor Goytema is a professor of industrial and operations engineering and civil environmental engineering at the University of Michigan. His research is highly interdisciplinary. Much of his group's recent work is focused on the problems of urban and infrastructure resilience and sustainability in a changing climate. And if you remember, we had a question about climate with our very first speaker, Terry McAllister. His research is grounded in risk analysis, particularly data-driven risk analysis and complex system simulation. So Seth, thank you for joining us. The floor is yours.
Thank you. Well, I'm Seth Goytema from the University of Michigan. So I'm going to be talking about resilience, equity, and behavior, particularly in urban spaces. So my starting point is that resilience is fundamentally about people. It's not about infrastructure per se, but it's about what they need to survive, return to normalcy, and ultimately thrive and achieve their potential. We also have to be very concerned about inequities in resilience. Which subgroups lack resilience and why, and what do they lack resilience with respect to? How does this impact them over the long run? And then the second part of the talk, I'm going to give a brief overview of a large chunk of research that we've been doing on the behavior side. And the starting point here is that individual behavior matters at the macro scale. What households and businesses do, particularly between events, can really impact the overall community, and particularly its vulnerability in rather profound ways that are difficult to predict up front. I also believe we need open source methods for using open source data to help communities best prepare and improve their resilience. And all of this is, of course, going to require an awful lot of computing power. So that's kind of a theme that will run through this, though I'm not going to dig into that part that much. So when we look at the research literature, there's really kind of two dominant views on resilience. And there's lots of variations on these themes, but one focuses on adaptive capacity. So this is more grounded in sociology and geography. So it really focuses on measurable variables that are either correlated with a community's ability to adapt or provide estimates of vulnerable subpopulations within that community. There's relatively little connection to provision of key services or infrastructure performance after disasters in many of these approaches. And then there's the engineering infrastructure approach, which is really grounded in an engineering perspective. And I trace a lot of this back to work coming out from kind of the 90s into the early 2000s, for example, the work in MCER, the Multidisciplinary Center for Earthquake Engineering Research that I was part of as a postdoc. But here, this really focuses on critical infrastructure, water, power, transportation, et cetera, and looks at an aggregate community-wide level generally. There's relatively little attention paid to spatial detail, specific subpopulations, or adaptive capacity at that individual level. So just a couple examples of these. On the left, we see SOVI, which is the Social Vulnerability Index. So probably a lot of people have seen this. This is their county level version of this. So you measure a bunch of different variables, and this is supposed to give you a measure or an estimate of the adaptive capacity of the population at that county level. On the right, we see more the engineering approach. So we have a recovery curve. This is one from the People's Framework from 2010, but we've seen these in earlier slides as well. So this gives you a sense of kind of the two dominant ways that people have been looking at this. We've recently proposed a different, more integrated view. We're terming it equitable access to essentials as a way to look at resilience. So resilience is fundamentally about equitable access to essential services before, during, and after a disruptive event. And the essential services are community defined, not analyst specified. That is, the community knows what's essential to them, and this may vary from community to community. There's probably some commonalities, right? So we need energy, we need water, but there's other things that may vary community to community. And it's the means of gaining, the means of gaining the access is not the critical part, it's the access. So you might get your water from a centralized water system, or you might get it from an emergency water supply. Either way, you have water. Now, there's some reasons you might want that centralized water supply, but it's the access, not the means of getting it, that is the focus. And we place a particular focus on the most vulnerable and disadvantaged subpopulations. And we do this in a way that we can get household level resilience estimates rather than a community scale resilience estimate. So we want to get down at that household level so we can start to look at inequities in resilience. Okay, so we're going to take a little digression into access. What is access and how do we measure it? Well, urban planners have been working on measuring access to lots of things for a long time. Traditional aspects of accessibility are proximity, availability, acceptability, affordability, adequacy, and awareness. For now, we're going to focus on proximity because that one's necessary. It's not sufficient, but it's necessary to have access. And it's going to be proximity on traversable paths, accounting for different modes of travel. So we've published a couple papers in this area in urban planning journals, trying to improve how we measure access to make it much more fine scale. And of course, that comes with pretty significant computational challenges. So traditional approaches for measuring access, when you look at the urban planning literature, focus on proximity. They look at large spatial units like a census tract rather than that individual household levels. And partly that's a data constraint, partly that's a computation constraint. They often use arbitrary thresholds, 400 meters or 800 meters. And if you're closer to that, to the park or the school or the hospital, you have access. And they still sometimes use Euclidean distance rather than an actual routed network distance, and don't often differentiate by travel type. So what we did was came up with a way of using open source data to be able to estimate access to any point service, a park, a hospital, a grocery store, whatever it is, within a community at the scale of each individual building. So there's 4 key steps. One is getting the input data. So you need to know where the buildings are. You need to know your network. We use OSM, OpenStreetMap, and public building location shapefiles to get this. Then we have to define the access points, which is, okay, what are we interested in? Are we interested in grocery stores to look at food deserts? Are we interested in schools? Are we interested in daycare? And then we have to get the locations of those things. Then we use an open source router. We used OSRM for this. You could use other ones. We've used Google as well. To differentiate by travel mode. So walk, bike, drive, and where available, transit. And then we apportion the demographics to downscale back down to those building levels so we can start to look at differences by socioeconomic class or race or things like that. So we can start to see which subpopulations have better access. And an example of what this looks like, this was a paper we did looking at access to green space. So this isn't resilience yet. But we looked at access to green space in these 5 cities, so Baltimore, LA, Seattle, Atlanta, and Detroit, at the individual building level. And the red areas in these maps are those that have the worst access, and the blue areas have good access to green space. And then we can start to differentiate by characteristics of the green space. So on the right, this is safe parks. So we then got all the crime data for these parks and looked at the violent crime rates in the park and asked, okay, well, who has access to safe parks versus unsafe parks? So for example, if you pick the dark blue on the right-hand side, that's Atlanta, you can see that 60% of the white population is within 10 minutes walk of a safe park, but only 40% of the non-white population is. So we can see there's a significant differential between just based on race. Okay, so what about resilience? So the previous work provided a computationally tractable, though still challenging, open source method for calculating household level access. And the code to do that is freely available on GitHub. But now we can say, okay, well, we can calculate access. So now let's extend the routing algorithm to account for damaged transportation systems. Let's account for water, power, and other centralized services and their impacts, both on household level and on those other centralized services. So if I lose power, it might not matter if I have access to a grocery store because a grocery store might not be open unless they have backup power. We need to account for building level damage at those service points. And then we need to simulate for future events or measure for live or past events access to services. So when we look at the centralized infrastructure, one of the challenges with trying to do resilience estimation for infrastructure is that the really detailed topology data, so for example, for the power system, is just not available publicly. We do a lot of work on power outage prediction with utilities and can get access to their data some of the time. But if we want to do this at scale across lots of communities, we need a way to estimate the very detailed building level performance of that power system without having access to the actual topology. So we have a paper that's under a second round of review now, where we first build a synthetic power network to service all the buildings. We put in all the components. We assign the lines to be overhead versus underground because this matters a lot in some types of hazards. Then we have a fragility curve for each asset, simulate the hazard loadings at the asset level, simulate the damage state of each asset, and then calculate the building level service availability based on that overall system state. So we've done this for water, power, and cellular communications and are starting to work on others. So this lets us get that centralized infrastructure in here in a way that we can still get down to a building level estimate. And it's a probabilistic estimate because there's a lot of uncertainty in this, in a way that we use only publicly available data. Okay, so now let's go back to the EAE framework. So this is an example of using EAE to look at an actual event and look at access, in this case, to food. And this was supermarkets. So this was Wilmington, North Carolina, and Hurricane Florence. So we've got a snapshot in time on the left, the map. The red grocery stores are closed, the white grocery stores are open, and the darker areas are those where they have less access. That is, it's much further for them to get to food than it is the people who are in the lighter colors. And you can see how this changes over time. So on the lower right, we have that kind of typical recovery curve, but now we can look at as a probabilistic probabilistic access, and that we can look at which fraction of the population are within certain distances of an actual functioning grocery store at a given point in time after the event. And then up above, we can then see how this changes over time. And this is that same empirical access function. So for example, if 4 kilometers was our, we thought that was acceptable, then on September 18, about 55% of the population is within 4 kilometers of a grocery store. Okay, so far, the EAE framework plus the access calculations allow us to estimate household level access to 2 types of services, really. Network provided, so this is what we think about from the engineering perspective, water, power, et cetera. But also discrete point services, which are also really critical to getting a community back up on its feet. So food, childcare, healthcare, emergency services, these sorts of things. This approach is highly computational, but so far we've implemented it at the county scale for a sizable county, approximately population of 1.4 million, and we're working to extend that to a much larger scale. This gets us beyond focusing only on critical infrastructure. That's important, but we have to also consider the other things that this community needs and alternate ways of providing those same services that critical infrastructure provides, be it backup power or emergency water supplies and things like that. It also lets us get down to a much finer spatial scale so we can start to ask questions about inequities in access over time by different types of service. Okay, so then the question is, where does behavior come in? No behavior so far in what I've talked about. Well, if we look at this kind of whole emergency response and preparedness cycle, behavior comes in lots of different components of this. So immediately before, during, and immediately after the event, of course, behavior is critical. So this is evacuation, rescue, all of these sorts of things. Then in the very short term after the hazard, then behavior is also really important. Infrastructure restoration, temporary housing, and things like that. Those 2 parts of behavior have been really pretty well studied. There's still, of course, a lot of unanswered questions, but we have a pretty good body of knowledge there. Where there's less information is on that longer term. So after you're through the recovery and you're in that in-between period, behavior still has the potential to influence how the vulnerability of that system, that community evolves. So that's the part that I'm going to focus on. We've been doing a lot of work in this area in the context of hurricanes, wind-induced damage primarily, riverine flooding, and tsunamis. And we've done this both with agent-based modeling and with cellular autonomous modeling. So computational models of behavior at fairly large scale. So for some of the hurricane stuff, we're modeling entire regions with hundreds of thousands of households. What I'm going to talk about today is some of the tsunami modeling that we did in Japan. So in particular, looking at the impacts of hard protective measures on community vulnerability. So this is work with Tom Logan, now a professor in New Zealand, Jeremy Bricker, who will be joining Michigan in civil engineering soon, and myself, published a couple of years ago. Okay, so there's this debate in kind of disparate bodies of literature about hard protective measures. So some claim hard protective measures offer false sense of security. And this is termed the levee effect, often in the urban planning literature. Others claim the best way to reduce flood and coastal risk is through protection strategies. Engineers in practice often will continue to recommend defenses against a 1 in X year event, 1 in 100, 1 in 500, 1 in 1,000, depending on the situation. So the question is, in this paper, do hard adaptive measures increase or reduce vulnerability, and more, under what conditions? So our approach to this was we took an approach grounded in risk analysis. We simulated behavior using a cellular autonomous model, which is a relatively simple version of a land use change model. We included idealized empirical human behavior that was based in studies that other people had done on behavior after these sorts of events. And then we analyzed the community's evolution over time to see how its vulnerability changes. That is, we look at not just the hazard, but also the community itself and how it changes. Okay, so how does this work? Well, we have our case study data. I'll talk about that in a minute. We develop a synthetic tsunami library, and we have a full hydrodynamic model of tsunamis. Then for each year, there is either a tsunami or not. And in our case study community, they occur on average about once every 40 years, roughly. We generate a tsunami with a given height. We have a building fragility. We get a damage count if there is a tsunami. But every year, even if there's not, there's potentially change in population and where that population lives. So our case study is Taru, Japan. So it's in northern Japan, very heavily impacted by the 2011 event. This is Taru before and Taru after. And I remember visiting Taru about 3 years after the event and standing on a hill, kind of in the middle upper portion of the right picture in the hospital. And it's just amazing how high this tsunami was. We were up on a significant hill and I still looked above my head to find the mark on the wall where the water had come. So this was a really, really damaging event. And they had seawalls. They had pretty substantial seawalls. Okay, so we have a hydrodynamic model of the tsunami impacting the area. So this was primarily done by Jeremy Bricker. So we can get tsunami depths at each point in the community. And we can do this for a bunch of different types of tsunamis. We then developed a synthetic tsunami library based on the fault and how that fault might move and how that translates into tsunami initial depths and how that translates then to the shore. So we get a bunch of different tsunami models, each with a different inundation depth at each point in the community. And I should point out, this is a pretty hilly area, and that comes to play in our land use models. Okay, so then we have to model the behavior part, that is the actual land use change. So this is based on transition potentials in the CA model. So we divide the area up into grid cells, and then we ask what's the likelihood that a cell will develop or undevelop, meaning people move out. And this is based on the neighborhood, what's around you, the awareness of the tsunami. So this is where the behavioral study that we had access to comes in. The accessibility to the ocean and the road, and in particular, the accessibility to the ocean is really important in these communities because these are fishing communities and they very much want to live close to the ocean, preferably where they can see it, so a seawall is a problem. Suitability, so there's a steepness constraint because this is a fairly mountainous area, and then a random effect. And this is based on the work of White et al. And others, which it's a somewhat common way to model land use change. Okay, so just to give you a sense of what this looks like, on the left, that's the development potential. The brighter the pixel, the more likely it is to be developed. Then you can see a tsunami come in, and you can watch the area where the tsunami hit and see it slowly get brighter as the memory of that tsunami fades over the years. Okay, so the first thing we did was ran this for 300 years and just imposed different heights of seawalls. They didn't change during the simulation, just up front said, okay, no seawall, 4 meter, 8 meter, and 12 meter. 12 meter is higher than any of the historic events that they've had. Okay, so the 0, 4, and the 8 all converge to about the same place in terms of the expected number of buildings damaged. The 12 reduces the damage. There's still some damage, and we'll see why in a minute, but there's some development on the outside of the seawall that's closer to the ocean. Okay, so that would seem to be case closed, right? Hard adaptive measures protect us. We build a big enough seawall, it keeps everything out, and it's only the people that choose to live outside the seawall that then have impacts. But what about how that community evolves over time, right? Thinking that they're safe, they move into a given area. What happens when we see an event that maybe we haven't seen before that we don't expect, a so-called black swan event? Well, we need to look at the community's development pattern. So in these maps, green is high likelihood of being developed and blue is low likelihood of being developed. And to make sure we weren't just making up land use change, we went back and we got historic aerial photography of the area and compared our model estimates of where people would be living to what the maps were. And we actually did quite well, except for one swampy area in the south part that we didn't account for it being swampy in our model. But with no seawall, the model suggests that people move out of the community and they move up into the hills where they're safer from the tsunamis. With the 12-meter seawall, they basically stack up behind that second seawall. So the black X is the seawalls that were already built in this community. And the second one is big enough to keep most of the historic, I think all the historic events out. So they stack up behind that where they're not experiencing any tsunamis. They're right by the road, which is the white line running through the community, the center of the community. And you get a lot of development there. So the presence of the seawall really impacts where people live. So they build behind these walls because they feel safe. So this is the levee effect. But what happens then when we see an unexpected event as a black swan? Well, the idea behind the levee effect is that adaptive measures encourage development in places vulnerable to large events because they prevent the learning that can happen from the small frequent events. So we kind of cut off the distribution. We get rid of all those small events so people don't see them. And then suddenly they get something that they've never seen before and they felt safe from it. Okay, so now we can run this and let's impose some bigger tsunamis on there. So the 4 sets of bars on the left up to the 10.66 meter tsunami, those are all within the historic realm. And they're all less than that 12-meter seawall. And you can see that 12-meter seawall, the green box plot, is lower than that 8-meter. So relative to the 8-meter, the 12-meter reduces damage. But when we go to the 13 and the 15-meter high tsunamis, we can see that the damage is higher, in fact, much higher with a 12-meter seawall than with the smaller seawalls. So when we look at those highest tsunami levels, the blue and the red, the smallest seawalls actually give us the least amount of damage because people have had a chance to learn from the smaller events and then move out before they get hit by the big event. So we get this displacement of people when we have this 12-meter seawall so that they're then at risk from this much bigger event. Okay, so a few concluding thoughts from the tsunami project. Communities evolve. They're not static, and we need to stop pretending that they are static when we design protective measures. Now, sometimes we'll impose some scenarios, but very rarely do we really close the loop and ask, well, what's the behavioral feedback from the protective measure to what the community's doing? This project looked at it in the context of land use change. We have other projects where we're looking at it more at that individual household level. What's the feedback to what you do to your house to help increase its protection against wind, for example, in a hurricane? How does that feedback to loss at the community scale? And there's potentially really large feedback there as well. So behavior really matters. Just building bigger and better hard protective measures can actually leave a city more vulnerable to those black swan events, the stuff that they haven't really considered very well. And there's a pretty robust body of literature developing on black swan events in the risk analysis community. And really, a city is not truly sustainable, but has to keep rebuilding after each damaging event. We need to think about this differently. Some more general concluding thoughts. Resilience is really about the people. It's what they need to access to thrive and to achieve their potential. And one way to get that is centralized infrastructure in some cases, but it's about a lot more than that. We also have to really carefully consider inequities in resilience. Ignoring those subpopulations with limited capacity to respond or particularly strong vulnerability can really cause generational long impacts. And I think we see some of that if we look at what's happened after Hurricane Katrina. And again, behavior really matters. Those individuals respond based on their perceived risk, their coping ability, their goals, and their information to take individual actions that really can affect a community quite a bit in the long run. And we need to make sure that we're not misestimating resilience in the long run by ignoring that behavioral adaptation. I will stop there and take questions.
All right, Professor Goikema, thank you very much. Very thoughtful, very interesting presentation. And on the outside looks so different than everything else that has been presented so far, but at the basis is a lot of computation to reach kind of the conclusions that you've reached. There are a number of questions, so I'm going to read them out for you. The first one is from Professor John Vandelint, and it says, thank you for the interesting presentation. Could you please explain how the census socio-demographics enter into the access modeling? For example, you showed white and non-white persons by location access, but not by income, education level, etc. Are those accounted for somehow, example, logistic regression or others? If not, are there plans to do so?
Right, so the way we do it is we get down to that household level access to whatever services that we're looking at. For example, let's say we're looking at food, access to food after a disruptive event. And then we need to apportion the characteristics of that area down to the household level. I showed racial characteristics, but we also have education level, income, characteristics of the household in terms of over 65 or not, things like that. So it's an issue of getting the data and then doing that apportionment so you can try to understand, well, what portion of my older population doesn't have good access to food or good access to healthcare? What portion of my lower education folks don't have access to these things? So yes, we can parse that out by different characteristics. I just showed the race one as an example.
Okay, thank you. Next question is from Professor Jamie Paget, who says, hi, Seth. So just reading literally, I appreciate your emphasis on estimating infrastructure provided services and characterizing associated inequities. At the core, this requires household level infrastructure models. You mentioned generating synthetic infrastructure systems and using open source data to enable this. Can you elaborate on the general approach, type of assumptions or uncertainties introduced in this process?
Sure. So this is an active project that we have going on. The first paper is under review. We've got a couple more coming. Now, of course, if we have the actual system, then you don't need to generate a synthetic network. But in most cases, we don't have the actual system. So let's take the example of a power system. What we do is we get that same shapefile of where all the buildings are, and we make the assumption that everybody has electric service. In the US, it's pretty reasonable. Then we make some assumptions. we know where the substations are, that's publicly available. And we focus on that distribution system because the transmission system is generally reasonably publicly available with some approximations. Now the distribution system in much of the country, but not everywhere, tends to be more radial. Okay, so let's grow a synthetic system that connects each substation to each house in a way that makes it look like a more realistic system. And then let's do an ensemble of these so that we can, because we know that no one synthetic network is going to be exactly right. So let's do an ensemble of these so that we can then try to capture some of that uncertainty. Then we go in and we put in, for example, let's say we're interested in a wind event, the power poles are really important for that. And if the lines are overhead or underground. So then we have a machine learning model that estimates if they're overhead or underground based on a whole bunch of characteristics that are publicly available. That part's actually remarkably accurate. And then we attach a fragility curve for each pole, each transformer, each line, whatever the components are. And then we hit it with our wind field and estimate which components are out. And then we do the full performance modeling, either topology based or power flow, depending on what the situation is. So this is very computational. It's weeks of runs, unfortunately, at this point.
Thank you. The next question is from Dr. Terry McAllister. She says, Seth, great presentation, thank you. How do you aggregate household level analyses, physical, social, economic, to inform community resilience impacts?
So the way we envision this is that we start with stakeholder interactions to figure out even what are the services that stakeholders in that community feel are important, right? If we look at the Arctic versus Florida, we're probably going to see different things. So the starting point is, what does this community feel is important? And there's different ways. Okay, so you go through this whole analysis, there's different ways to do this. One is to keep it all separate and say, okay, we've got these different services. Which parts of the community have better access or worse access to these different services after which types of events? And that provides a lot of really useful information to the community. You can go then the next step and say, okay, well, let's aggregate this into some sort of overall resilience measure, but I think that loses an awful lot of that focus on the susceptible subpopulations and the particularly vulnerable subpopulations. But there are methods you can go through using decision analysis and other things to try and capture that and aggregate it into an overall measure. But I think keeping it separate at some level helps really understand those populations that might be particularly vulnerable.
Thank you. Next question is from Yong-Chol Lee. It says, hello, Dr. Goikema. You said that you use a lot of open source data. Could you share the links to the open source data that you used in your studies, especially the one related to the census tract level infrastructure availability?
I don't know of any open source data on infrastructure availability. That's where we use our synthetic networks. So we start from the, our main sources are shapefiles of where the buildings are. And in the US, those are generally pretty available, but different sources depending on which city. OSM is where we get most of our transportation information, though you can do it through Google too. You can scrape Google, we've done that. Costs you some money, but you can do it. We use ORSM for our router to do our routing by transit type. You can also do Google, we've done that too, or any of these others. So it really depends on which part you're talking about. And then we use a lot of census data and other sources for the social demographic data.
I do have a question. We have 1 minute left before we are scheduled to take our break, but you've mentioned multiple types of models. You have the transportation models, you have the power models, you have the people models and how they behave. Are these models that you've developed, or have you worked with others to develop these models and then connect them together? How did you achieve this interconnection between these disciplines?
So these are mostly models we've developed. So the behavior model, we work with behavioral scientists. So a lot of the behavior models came out of a large hazard seas grant that I was a PI on. We had 7 institutions involved, and some of that was really strong behavioral scientists and economists doing that part of the work. So we rely a lot on that. For the more infrastructure models, those are things we've developed in our group. For the tsunami model, that was our group working with Jeremy Bricker and his group in Sendai to try and develop that model.
Okay. All right. Well, thank you very much. Thanks again. And I think there are a number of other questions, but just to keep on track, I think, Seth, if you would like, you can go in actually and as a panelist and answer them. I think the other speakers also have that access to. But even if you don't, we are still collecting the questions and they will go into a pool for questions for discussion later. So thank you again very much.